So now we're going to talk about the actual piece of GPS hardware that we're going to be using for LACES and that you guys are going to use in your student payloads, unless you want to source your own and use it. So the one that we use is called the Ultimate GPS Logger Shield. It is made by Adafruit, which is a company that makes, sort of these hobbyist electronics for Arduino and Raspberry Pi type applications. So this is the logger shield that we're going to be using. It's actually stacked on top of a smaller Arduino called an Uno right here. That's why you don't see it sticking on the end. But this is the actual unit, and hopefully everyone has one of these so they can use it for the upcoming hands-on activities. So you sort of have a few major components here. So this is just a view from the top. You have a socket here that the micro SD card, because this is also your SD card, that's the logger part of it. You have a connection for an external GPS antenna. So there's a very small connection right here that you could then connect a cable to run a external antenna to. And, the only time we've really needed to use that was when we had a payload that was actually metal. This was not on a LACES flight. This was a larger balloon platform where we had the weight, and our payload housing was basically made out of sheet metal, and sheet metal is really good at blocking radio waves. So we needed to put the radio signal outside. But for most of cases, hopefully you'll just need to use this internal antenna. So that's what this little piece of ceramic is right here. And then underneath it is the actual chip that runs the GPS. And then you have a slot here for a coin cell battery. So this thing actually has a real-time clock built into it. And in fact, it will automatically set that real-time clock off of the GPS, which is nice because that means you will still potentially have a timestamp information even if you lose a fix. And then you have this central area that is just perf board, and the idea here is if you have a relatively small simple circuit, you can just build it on here rather than having to get a separate prototyping board, or if you have some sort of breakout board, this would be a good place to put it. So as I talked about, there is a built-in patch antenna, but sometimes depending on your shielding, or maybe you have something that's close by that's interfering, you might need to have an external antenna. So you have this, again, I'll stress, very small antenna connection right here. So if you look, these are little surface mount LEDs that are very small, and it's about the same size. So this is called a UFL connector. Most of the time, if you have a antenna, it will use something called an SMA. That's just the particular shape of the connector. So you'll probably need an adapter if you're going to use an external antenna. However, the GPS unit is designed to automatically detect and switch over to the external antenna. And in some of the GPS or some of the NEMA sentences, one of the pieces of information that it will output is it will tell you if it's using an internal antenna, if it's using the internal patch antenna here, or a connected external antenna, or if there's something wrong and it can't connect to an antenna. So as I said, this does have a real-time clock built in, and it has a slot for a coin cell battery. And the idea with that is you may lose a fix, but you still want timing information. So when the GPS has a fix, the real-time clock will get set by the GPS to the current universal time code timestamp. If you lose power, the battery, assuming you have a battery installed there, will maintain power to the real-time clock, keeping your time up to date. However, if you so that means if you lose power and you come back, you will have timestamps even before you get a fix. The GPS, has a built-in RTC, but it doesn't have the capability to maintain power, which would mean that if you lost power when it came back, it would go back to, midnight, January 1st, 1970. And what this battery does is it maintains that power. And just to make sure everyone's clear, there isn't a separate RTC chip. It's built in to the GPS unit. It's integrated in there. So really, the big thing here is this coin cell that's providing that backup power to that clock. You have a few different indicator LEDs. There's obviously a power LED. If that's not on, the shield is not getting power, so it won't work. You have this L13 pin that is on the clock that the SD card line is on. So basically, this will blink when you're doing, and it will blink very quickly when you're doing stuff with the SD card. When you first turn it on, it will be solid as the Arduino boots up. And then the third LED you have is this fix LED, which allows you to tell if you have a fix or not, which is very useful, for example, when you are powering your payload on the flight line and so you can't really hook your payload up to a serial port because, you're just doing a quick power up and you're not allowed to bring a computer on the flight line. But you want to know, hey, did I actually get a fix when I started up? So it basically has two modes, a fast blink and a slow blink. So the fast blink, it'll blink on and off every second, which indicates that you do not have a fix. And if it's blinking noticeably slowly, so once every 15 seconds, that means it does have a fix. Like I said, you also have this prototyping area, which is useful for building, whatever kind of circuit you would possibly want. One thing to note is these are just through-hole solder pads. There's no connection between them. So if you're going to build something on here, you're going to also have to solder little jumper wires to go from hole to hole. And then one thing that's potentially important is you have this little breakout area right here that has specific pins on it. It has a 3-volt output because the GPS and the SD card actually run on 3.3 volts. So there's actually a level shifter, which is right here, that actually shifts all of your signals from 5 volts to 3.3 volt logic. And so all that is there's a 3.3 volt reference right here. You have a pin that basically tells you if you have an SD card installed or not, which is useful and is actually used in the background by the SD card libraries, right? So if you're trying to write, you want to be able to tell, oh no, there isn't a card actually in there. You have this chip select line, and that is used by the particular communication protocol that the SD card uses. So that is what tells the SD card, hey, I'm talking to you. You have a pulse per second pin. So there is a standardized pulse once per second as part of most GPS units. And this is very useful because if you have multiple things that have a GPS, they will all be pulsing at the same once per second, because the pulse is actually coming from the GPS signal. So that is primarily used in trying to synchronize multiple things. And then you have the transmit and receive lines, which are the GPS transmit and receive. So the way that you actually talk to the GPS is through a serial library, through a UART protocol. So this is just like the transmit and receive that you used through the USB to talk to the SD card. So this is where you're going to connect to, your TX1 or RX1 or 2 or 3 lines. And then you will probably notice there's a switch here that has one position labeled as direct and another position labeled as soft serial. So that is set up so that you can talk to the GPS shield 2 different ways. And what the switch positions mean is direct connect or software serial. In particular, the direct connect connects to the serial 0 channel, right? The pins on the Arduino that are just labeled TX and RX with no number. The issue with that is the same serial port that the USB port connects to. So it's the same one that your sketch uploads get transmitted to. It's the same one that if you are trying to use the serial monitor, that stuff gets written out on. So because of that, oftentimes it's useful to basically shift the GPS communications to a different serial port. And that's why you have this software serial. And the idea is you put the position, the switch in the software serial, and then you would connect this TX and RX pins to one of the other serial ports. In particular, the reason this thing is called software serial is on the Uno, which is kind of the same size, which was basically sort of the baseline Arduino that this shield was developed for. You do not have a serial 1, 2, 3, and 4. You just have the one hardware serial, and then you can do basically a software-based serial on different pins. So as I talked about, when you have it in direct connect, which is down in the way that it's shown here, it connects the transmit and receive pins from the GPS chip, which are on these two middle pins right here, to the lower set of pins right here, which will go over to the two pins here that are labeled 0 and 1. And if you had that sitting on top of your Arduino, you would see that this pin 0 and 1, and in fact, if you have your Arduino handy, you can look at the two digital pins that are labeled 0 and 1 are the TX and RX pins, i.e. the serial 0. So one thing to note is basically while that's going on, you will not be able to upload code to the Arduino, basically because the GPS is going to be talking over the exact same time you're trying to upload code, and they're just going to get scrambled. So if you're trying to upload code, you want this thing sitting in the software serial position. You upload your code, and then you can put it to direct and use it if you want to use it that way. But one thing that can be useful for is when you have it in this direct connect, it's transmitting the GPS strings over that same serial 0. So that means if you open up the serial monitor and this switch is in the direct connect position, you will be able to see what the GPS is actually transmitting on the serial monitor. But what we're going to want to do in this case is basically use this in the software serial position, especially because on the Mega that we have 3 other serial ports that we can use to talk to. So just to make lives easier, we're going to want to make a jumper and connect from that TX and RX pin of the software serial to one of the other serial ports that we have on the Mega. And in this case, you can see, so this is the connection from the TX and RX here. So you can see TX is on top, RX is on bottom. And so the red or the blue line goes all the way here from the transmit pin to the receive pin, so RX1. So in this case, we're using serial 1. And then the orange pin does the opposite, right? So, like I said, we want to use it this way. We need the switch in the up position, which is going to connect these middle pins to the top pair of pins, which are connected to these 2 holes here. And this basically deconflicts the serial and the GPS and your Arduino USB serial port. So the way that this thing actually works on a software level is the GPS just spits out these strings, and the serial library has a buffer that all of those characters get written into. It just automatically knows that, hey, a character just got sent. Let me take that character and put it in this buffer. And it's just going to fill up this buffer. If you don't do anything, it will eventually completely fill up that buffer, and then you're going to start losing information. So there's two different ways you can go check that buffer and read the characters out and clear them off of the buffer. The first is called polling, basically where in your program loop, you would just go check and see, hey, is there anything in the buffer? If there is, let me try and read it. The other way is having an interrupt. And the important thing here is if your program gets busy doing something else, you may not get to the part of your loop where you go and do this check, right? So if the only thing I'm trying to do is read the GPS, the polling is probably fine. But if I'm reading the GPS and I'm doing a bunch of other stuff where I'm like reading my other sensors, and if there's the potential that can take a long time, I might get busy and my buffer might fill up and I might lose information or get a garbled string because it's starting to overwrite itself. So the way you avoid that is using something called an interrupt, which is you have a specific signal in the code. It can be, hey, this pin gets flipped high, or it can be, based on a specific register, reaching like a counter that is automatically incrementing, getting up to a certain value. And what that does is it interrupts the flow of your program. When that signal gets received, the Arduino stops whatever it's doing and goes and does whatever is what's called attached to the interrupt. So, and this is sort of an example in plain terms, right? I can go look for my package. I can just go check it. Or I can be doing a bunch of other stuff, doing the laundry, and then when I hear the doorbell ring, I stop what I'm doing and I go check for a package. This is an interrupt, and this is sort of the recommended way that we suggest you try and read out the GPS. It's a little confusing and hard to understand. But if you use this code as written, it should work. So the key thing here is you have this function here, signal, and what it actually, the argument here is this timer 0 comp a vect. And this is a little bit in there, but this is actually a internal register of the Arduino that's fed off of the clock. So basically there's a counter that counts every time the Arduino does a clock cycle. So it just ticks up every single time it does anything. In particular, it's the one that's used for counting the millis function. So down here, we're basically checking, hey, if that timer gets up to a certain value, stop what you're doing and go read a GPS character. Read a single character off of the GPS buffer. And if there's nothing there, it just won't do anything. So basically, this is ensuring that you are checking the GPS buffer every millisecond, no matter what you're doing. And that's important because, you can see you have these strings that are, 20 something characters long or longer. Uh, Usually this is sent out every second, and you can be sending multiples of these out. And, depending on if you were to skip a data transmission and not read all the data out, you may not, you may overwrite and fill up that buffer. So this is just an example of what the output you get from the GPS. So like we said, you're going to get NEMA sentences. What NEMA sentences you get depends on what you've asked for. So by default, it will transmit a certain set of these NEMA sentences at a certain rate. But you can send commands to the GPS telling it how fast you want that information and, what specific information. And for example, one of the RMC sentences that it got, so you can tell that it's a NEMA sentence because it has this $GP. The RMC here tells me it was a RMC sentence. The first thing, if you were, you probably don't remember, but if you were to pull it up, you would know, okay, this is the time stamp right here. This was a status flag. And then it's sort of, the rest of the information isn't particularly useful because there wasn't a fix. So it's just going to give you a bunch of zeros and blank entries. So in particular, you can use the actual GPS library to do a lot of the heavy lifting for you. So as you do the character reads, it's going to copy this character from this NEMA sentence, character by character, into an internal variable of the library. And basically, when it gets to the end line character, it's going to realize, oh, I have a complete sentence, and it will tell you there will be a Boolean value that gets set to true that says, I have received a complete NEMA sentence. And then there's a function that you can call that will basically parse this whole NEMA sentence and look at the pre-formatted sentence, so it knows what it does, and copy the different values into the these internal variables. So if you call the parse on this function, it would then basically populate all of these variables. So in this case, this GPS is the base class. So this is like the serial that we use during the with the serial port objects, and then you have all these dot whatevers, so you can then access these variables that are part of this GPS class. So if after I've parsed this, I call GPS.day, it would return 15. That's coming from this 15 right here. The month comes from this 08. The hour comes from this 21. But the point is you can use the library to do a lot of the heavy lifting, so you don't have to manually try and format.